6.5 exponential change in separable differential equations. Before we get into some specific examples, let's clear up some points. First off, get out my pen. First off, what is a differential? Well, we've been using them all along, but maybe a little review it would be appropriate. When we look at a function and we think about, well, what is the slope between this point and this point? Well, we have the rise over the run. We have a change in x and a change in y, and that slope then between these 2 points is just delta y divided by delta x. Okay, the change in y over the change in x, rise over the run. And that's how we use to calculate the slope between 2 points on a function line. But if we wanted the slope at one point, kind of what is right there at that point, what is the slope? Well, that gets into the idea of a derivative. And what we did was we said, allow us to go and think about extremely small changes, infinitesimally small changes in y over infinitesimally small changes in x. This is a differential. This is a differential. And the nice thing about representing a derivative in this way, in Leibniz notation, it allows us to manipulate the dy and dx algebraically, which for the most part is going to work out for us. Okay, so that's what a differential is. It's dy or dx, and we've used that in definite integrals and things like that. So we're kind of familiar with that. Now, what is a differential equation? Well, I wrote down a definition here from Wikipedia. It says a differential equation is a mathematical equation for an unknown function of one or several variables that relates the values of the function itself and its derivatives of various orders. Whoa. Well, let's back up and say, well, what is a normal equation? Let's hold on differential equations for a moment. What's a normal equation? Well, I'll write a normal equation. X minus 3 equals 0. We can solve this equation and we get x equals 3. So we get a number for an answer. Well, what's a differential equation? Well, here's going to be a very simple one that's used in the book, and we get dy dt is equal to ky. Okay, well, here is a function and its derivative. Okay, so this is a differential equation. Now, when we solve this differential equation, and we'll do that here in a moment, we are not going to wind up getting a number for a solution. We're going to wind up getting a function for the solution. In other words, what function of y makes this statement true? Because as soon as you say this, okay, as soon as you say this is true, there is a function that satisfies this relationship. We want to know what it is. Now, where does this equation come from? This particular one? Well, let's imagine we wanted to model population growth in invasive species. This is a species that just arrived in the United States. It has no natural predators or diseases. It's fairly rare to start with, so it's got plenty of food, and it's growing in fact, its growth is only limited by the number of females and how many offspring they can have at one time. Well, so for our model, we say to predict what's going to be happening in the future, let's just say that the rate of increase, the change in y over time, so there's our y is going to be our population size, and t is going to be time. the change in population size over time is equal to some constant times the current population size. Okay? And we say that's going to be a reasonable estimate. Will it work forever? No. But is it going to be a reasonable estimate for now? Well, we're going to claim it is. Now, if that's true, then what will the population be in, say, 20 years? How would we figure that out? How can we come up with something so that we can say the population in 10 years will equal some number? How are we going to solve that? That's what differential equations are all about. We come up with some basic relationship between a derivative and a function, and we then try to extract from this a model of what's going on.